Hi, my name is Al Palmer, and today I want to talk about how to get quality sound a long distance without having any interference or very minimal interference from electronic devices and stuff that can interfere with good quality audio. So I'm going to explain to you what happens inside a guitar and how we can get that audio into a mixer board as clean as possible. So generally speaking, the guitar has a pickup that's built in, or several pickups like this guitar, and they are wired to a connector which is hooked up with a guitar cable, typical guitar cable, has a 1/4-inch phone plug jack, and it's only got a ground and a single conductor. And you plug it into the guitar, and you plug the other end into your amp, and off you go. The problem is if this cable isn't of high quality, if there's a lot of electromagnetic interference in the building or in the room, fluorescent lights, motors, high-speed power supplies, all that kind of stuff, they can interfere with the operation of this cable, and that can put some distortion into your audio, or hum or buzz or something like that. So I'm going to show you how to minimize that. And if you're using a single-ended source like this is called an unbalanced source, which means ground and one wire. You should keep these cables to a minimum, usually less than 10 feet. If you're going longer than 10 feet, this cable begins to act like an antenna, and it starts to pick up noise from around the room. I'm going to show you what you can do to help improve your audio quality. So this device here is called a direct box. And a direct box takes the single-ended audio source, which plugs in here, it says guitar input, and then has a Canon connector output, which is a cleaner source of sound. And I'm going to explain why the Canon connector and its dual balanced output is higher quality than the guitar cable. So the schematic symbol of the guitar pickup is like this. It's a signal generator which has a wire come out, and there's some tone controls and some volume control circuitry and stuff like that in there. But it's basically a grounded wire, a shielded wire with a single signal on the single center conductor. And to symbolize that, they draw a circle around the wire and ground that, and that shield is hooked to the same place as the ground, and so you have all of your signal on the center conduct wire, and that's what the guitar cable is. Now, if you go into a direct box, then the direct box, I'm going to play some games here. We're going to pick a dotted line, which is here, and I'm going to show you what is in the direct box so you can see inside the direct box is this. It's got a transformer, which is connected back to ground, and the output of the secondary of the transformer, which comes out like this, does not have a ground reference. There is a ground reference, but it's carried on a third wire. That's why these connectors, if you look at them, these are Canon connectors, have 3 conductors, male and female. The output of the direct box is a male, and you would plug the female connector in here. And what you have is the 3 wires, 1, 2, and 3, and they're both have signal on them. But because they're on opposite ends of the transformer, these 2 signals are 180 degrees out of phase, like that. So you have 2 hot wires, signal on 2 wires instead of just signal on 1 wire, and a ground wire coming through at the same time. Now, this wire can now be 100 feet long, even though that signal is maybe only 100 millivolts or 1/10 of a volt peak to peak. It's very small, but here's what happens. At the other end of your 100-foot cable, you have another transformer. The other transformer then has a secondary with one end grounded, and you get the same signal out here that you put in over here. Now, here's where the magic happens. With an in-phase signal and an out-of-phase signal, both on these 2 different wires, what happens is any kind of electromagnetic interference from the lights, motors, that kind of stuff, is put on this in phase. Now, notice they both go positive, they both cross zero, and they both go negative at the same time. Both wires are exposed to the electromagnetic interference for as long as 100 feet or more. This signal that's induced into the wire can actually be bigger than the signal that you want, the signal coming from the guitar pickup. But what happens is when it gets to this transformer, the two in-phase signals have no differential voltage across the primary of the transformer. When that happens, there's no current flow and it's not transferred to the secondary. So what happens inside this transformer is common mode signals are ignored while differential signals are passed through. This is a characteristic known as CMRR. CMRR stands for Common Mode Rejection Ratio. And it's the ability of the transformer to reject the common mode signals while passing the out-of-phase signals. CMRR is a characteristic. There will be a minute amount of capacitive coupling, which may put some of this signal that you don't want over there. So that ratio is how much bigger is the wanted signal versus the unwanted signal. And usually it's around 1,000,000 to 1. 60 dB or 50 dB is 100,000 to 1. It's a very high ratio of the unwanted versus the wanted signal. So this transformer that's in the direct box, it looks like this. This is a direct box I've taken the lid off of. And it's as simple as that. Input jack, output connector, and it's just a little transformer with no connection between primary and secondary. And you can see this little black wire right here hooks the ground of the output to the ground of the input. That's the same as the wire that's going through here, coming from the ground. So the ground is passed through, but it does not have any signal on it, just the two hot signal wires. And they're labeled plus and minus in the Canon connector, so you can keep track of the phase of when this original source goes positive. The positive wire will go positive in sync, and the negative one actually is the one that's out of phase. And so they know which way the windings are made on the transformer, and so they can keep track of the in-phase and out-of-phase signals. When it gets to the other end, the same thing happens in reverse, and the common mode signals are rejected and the differential signals are passed through. This concept was originally used for the old-fashioned telephone companies, where you would have telephone lines with just volts of signal going underneath power lines which had hundreds of volts of signals, and you would induce a lot of unwanted signal into your telephone lines. But the telephone signals were out of phase and the induced voltages were in phase. And so what happened is when you got to the other end, you went through a transformer, it rejected all of that, and you didn't have any hum picked up on your transmission lines. So that common mode rejection is not a new concept. It's been around for a long time. And in fact, it's also used in even more modern forms of communication, like the Cat5 cable. And if you look carefully at a Cat5 cable, the Cat5 cable actually has, I think, 8 wires in here for 4 transmission paths, and they use differential signals on each wire, on each pair of wires, and the fact that they're twisted together so they don't interfere with each other allows you to have very, very high-speed data rates going through a Cat5 cable. And it's fairly immune to outside electromagnetic forces. So this concept isn't just old-style audio telephone. It's also used in high-speed computer communications as well. So this concept of common mode rejection ratio, using a transformer at either end, they have brought in electronic versions of this, and you can do this electronically as well as with the older school transformers. And that's what this device here is. This is also a direct box. It's a little more sophisticated than the other ones, but it's got the input connector is 1/4-inch phone plug, and the output connector is balanced Canon connector. And so this does the same thing, but there's no transformers in here. It's done with something we called an operational amplifier. And an operational amplifier is an electronic device but it's got dual inputs and a single output. And the two inputs are used because one of the inputs is an inverting input, known as the negative, and the non-inverting input is the positive. And this is a grossly oversimplified version of this circuit. But if I put a differential signal on here, in-phase signals will be applied to the inverting and non-inverting inputs at the same time and will be ignored on the output. But out-of-phase signals will be amplified. So a positive going signal on the positive input makes the output go positive. And a negative signal on the negative input also makes the output go positive. So you get better amplification of out-of-phase signals than in-phase signal. Once again, this is called the common mode rejection ratio. It's how well are we rejecting the common mode signals, which are the ones that are in phase. So we're getting rid of the hum and the buzz and the electronics in the room and just passing through the signals that are coming through 180 degrees out of phase. This particular direct box, it's known as, because it has op amps and other electronics inside, it has a battery. It has a little battery door here. You can put a 9-volt battery in here to run this. But the other thing about differential amplifiers and common signals like this is I can run power backwards through the audio lines and use that to power this device. So what happens is on the mixer board, here's your standard mixer board, and it has inputs for both balanced inputs and unbalanced inputs, depending on how far the leads are coming into the front of the board. And there's a switch on the board that says phantom power. And what it does when I put on phantom power is it puts like 20 volts on both of these lines, positive, in respect to the ground. So 20 volts comes backwards through your audio lines, and it does nothing inside the transformer because it's positive voltage on both leads. And if there's positive voltage on both leads, then there's no current through the transformer. But I can steal some of this power off as long as I steal the same amount from both sides, which is easy to do. And then the return is back to the negative. And I can use this to power the electronics inside the box. So a lot of your quality mixer boards have a phantom power button on it that actually sends the voltage back, and then the direct box uses that voltage to run its electronics. And the advantage is if you're using op amps instead of transformers to do the differential outputs or to recombine them, like what happens in the board once the signal gets there, is you have better frequency response if you can avoid the transformers. Transformers are never flat across the entire audio spectrum, and you can do that with electronic op amps, better than you can with transformers. So if you're trying to get audio a long distance without interference from outside electromagnetic forces, if you switch it to an unbalanced signal, which means you've got two wires opposite of each other, and transport it using the direct box, and then convert it back at the other end, you have a much higher signal-to-noise ratio because of the common mode rejection, and you get higher quality sound with less interference, and it's cleaner. And if you use the solid-state version, you haven't lost any frequency response at all. If you have any questions, let me know. Thanks for watching.